Thank you for watching this video clip. It's entitled Signal Integrity Design using Fast Channel Simulation and Statistical Eye Diagrams. My name is Colin Warwick, Signal Integrity Product Manager with Agilent ESOF EDA. The problem I'll address today is typical of pre-layout signal integrity design, namely how do you optimize the many transmitter, channel and receiver characteristics and settings to meet your design goal at the lowest cost. To evaluate even one set of settings, we need to compare the BER contours down to a low value, maybe 10 to the minus 10 or 10 to the minus 12, versus the eye mask, and then we need to repeat that simulation thousands of times. For example, if you have only 10 parameters, each with only 2 settings, an exhaustive search would take 1024 simulations. For real projects with smooth variations of the figure of merit versus optimization parameters, you can avoid exhaustive techniques, but still, the bottom line is you have to run a lot of simulations to find the optimum set of settings. Multi-million bit SPICE-like simulations are out of the question. They take far too long. Bit-by-bit channel simulation using brute force pulse superposition over the length of the channel memory is better. Maybe you'll get 1,000,000 bits per minute. But statistical channel simulation is much better. The simulation length need only be as long as the channel memories, the pulse response length of the victim and crosstalk channels, plus some time to perform statistical calculations that I'll go into later on. Here's a comparison of the techniques I discussed in the previous slide: SPICE-like simulation, bit-by-bit channel simulation and statistical channel simulation. This first row compares the methods. SPICE uses modified nodal analysis of Kirchhoff's currents law for every time step in every bit. It's quite expensive computationally. A bit-by-bit channel simulation runs a short SPICE simulation just to get the pulse response of the channels, and after that it uses bit-by-bit superposition of the step responses for each bit in the bit pattern. A statistical channel simulation does statistical calculations based on the short SPICE step response or pulse response. The statistical calculations I'll go into in the next slide. The applicability of the methods is shown in this next row. SPICE is very good for linear and non-linear circuits. Bit-by-bit channel simulation can only be used for linear time invariant circuits. It can be used for any specific bit pattern, and you can let the adaptive equalizer taps run during a bit-by-bit channel simulation. The statistical channel simulation again is only applicable to linear time invariant channels and systems. The bit pattern is fixed. It actually exhaustively covers all the bit patterns in the memory of the channels. It's a general bit pattern, and you have to fix the equalizer tapped. You can't let them adapt during a statistical channel simulation. This last row shows the advantage of statistical channel simulation. What BER floor can you measure in a 1-minute simulation? Well, with SPICE you may get 1,000 bits per minute, so the minimum noise floor you can measure is 10 to the minus 3 bit error rate. In a minute simulation of bit-by-bit channel simulation at 1,000,000 bits per minute, maybe you'll get 10 to the minus 6 floor for your BER. But the statistical channel simulation can give you an arbitrarily low BER floor in about a minute. To get these low BER contours in about a minute, we've added a new capability to ADS 2009 Update 1. It's a statistical mode for our channel simulator. Unlike competitors' point tools, Channel Simulator is integrated in that it acts on regular schematic and layout components that you use with ADS transient convolution and ADS momentum. You can model lumped and distributed elements, including elements with artwork like these lookalike components here. The sources are special binary sources where you can set the details of the binary pattern, the line coding, the equalization, the electrical properties, and the jitter. Likewise, the receiver is specific to signal integrity, and it lets you set the equalization and so on, including adaptive equalization like decision feedback equalizers. A new custom iProbe component works with both the channel simulator shown here and the traditional SPICE-like transient convolution simulator. You can drive the simulator manually or from the tuning, optimization or batch mode controllers. In bit-by-bit mode, Channel Simulator works in 2 steps. First we probe your schematic and the artwork, if there is any, using a single pulse source and the regular transient simulator. We pull in the convolution option if there are any components defined in the frequency domain, and appropriate EM simulators if there are any distributed or artwork, as we call them, layout components. The simulator need only run for a short length of time equal to the pulse response, or equivalently the channel memory. Step 2 is we use the pulse response and as a linear time invariant model of the channel, and then use signal processing superposition techniques to calculate the output for millions of bits without having to call the SPICE simulator again at all. In statistical mode, again we have 2 steps. The first step is the same we saw for bit by bit mode, but the second step is much quicker. There's no need for brute force superposition of each bit, just some calculation based on firstly the intersymbol interference and crosstalk implied in the through and crosstalk pulse responses, secondly the jitter specifications, thirdly the equalizer specifications, and fourth the line coding. So that's the concept. Now let's look at a demonstration.